Okay, let's continue with our study on the linear vector spaces, and we have already covered definition and some important property of a linear vector space in the first lecture. Let's go over some basic properties of linear vector spaces. So if V1 and V2 are the vectors, uh, and alpha is a number. Alpha is not visible here, so let me mark it. So alpha is a number. Then we have alpha into V1 into V2 is expressed as alpha V1 and alpha V2. If V1 and V2 are the element of vector space, then U defined like this should be also an element of vector space. This is how the name of the linear vector space come, because the linear combination is a element of a vector space. So we also have a unique zero element for every vector space, and it is important to note that we can always add two vectors, multiply a vector with the scalar, but we cannot multiply two vectors. This is because it's a linear vector spaces. Multiply two vector, it loses the property of linearity. So it becomes a square. Square is a violation of linearity. So that is why we only add vectors and do not multiply them. There is a caution about pure mathematics. It is logical, however, it should be logical, however trivial it may be. That is why we say that mostly there is no scope for intuition, but it is a mathematical induction. Mathematical induction is a very important method of proving various theorems and solving various problems. However, intuitions also has a lot of space in pure mathematics too. Of course, why I am saying this uh, is to highlight the difference between pure mathematics and mathematical physics. Let's look at the example of 2 into pi. What is the value of 2 into pi? For mathematicians, it is 2 into pi. There is nothing more to it. Pi is a rational number. On the other hand, engineer, physicist, and other people would like to have a number. It could be 6.28, blah, 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 and so on, or it could be 44 by 7, etc. It requires some numbers based on how much you want to calculate. You may truncate them, otherwise you would be going on forever and ever. In mathematics, there is no such concept. Pi is just pi, that's it. Of course, with this caution, we'll go ahead and try some of the example. Most popular and useful example of vector space is Rn. It is an n-dimensional real space. Of course, you could have a complex space too. That would also come under this. But let's, for simplicity, let's use a real space, and rest would be very similar. The vector here are tuples. For example, we often use R3 or R2, which can be easily generalized to Rn. So there is, to reduce the writing and complexity, you just use R2 or R3. R2 is even more useful because you can draw it on a sheet of paper. So the element of R3 is a tuple of three real numbers, and the scalar here is alpha is also a real number. So this constitutes a full vector space, set of all real tuples, three tuples, which would be our vector space. Or in the case of R2, it is two tuples which constitute a vector. Let's check whether it satisfies the property of vector spaces. Let's first let's add. Of course, this also serves as a definition of adding. Let V and U be a vectors in R3. The V is represented by three real numbers, V1, V2, V3, and same way U is represented by three real number, U1, U2, U3. Okay, we can define the addition of these two by simply adding the corresponding component of tuples. So that is, you write them and simply add them. At this stage, it is just an addition of two real number, which is also a real number. So the resulting of addition of two vector defined in this way would result in a tuple of real number, and that is what is our vector space is about. Uh, define addition in this way, the result of adding two vector is also belongs to our vector space, and it satisfies all the properties of the vector space. So that is how your testing goes. This may look very trivial, but this need to be done. Of course, let's look at the simplest example. Let's look at the example n is equal to 2. Our vector is a set of two real numbers. Let's take a specific element 3 and 4. Of course, we can draw this with the two-dimensional orthogonal frame. You have two axes, x and y. You take first one to the x-axis, go 3 points along them, and go 4 points along the x-axis. You can do reverse. You can go along the y-axis 4 point, 3 point, all that you can do, and you arrive at your vector element. Of course, the rest of the vector elements are defined all in this plane, and the entire 2D plane forms our vector space. Of course, here there is a possibility of defining our arrow for the direction and magnitude. The arrow is a direction connecting between the origin and the R2 space, R2 element, which we have used as a vector. Of course, let's go to the next important concept, which is multiplying a scalar to a vector. Okay, let's V be the vector, which is a three tuple of real number V1, V2, and V3. Let alpha be our scalar, which is simply a real number. Alpha times V is equal to, which we define as alpha into V1, alpha into V2, and alpha into V3. Again, at this stage, it is a multiplication of two real number, and each component would be a real number, and resulting a three tuple of a real number, which is in fact is our element of this vector space. And this shows that it is closed under the multiplication by a scalar. Let's look at one of the trivial examples, that is a special case alpha is equal to 0. When we multiply any vector by alpha, which will leads to alpha into V1, alpha into V2, and alpha into V3, since alpha is 0, all these elements tends to 0, and this is our 0 vector. The unique 0 vector is given by a vector 0 with the hat is an element 3 tuple 0 0 0. So that is our 0 element of this. Again, this satisfies all conditions of 0 vector, and this is essentially shows that we have a full vector space which satisfying all the conditions of the. So let's look at the scaling once again pictorially. So we have our element 3 and 4, and then let's take alpha to be 0.5. We take multiply both these component by 0.5, and that results in a new vector, which is v1 which w1 w2 is 1.5 and 2. So we mark it on the real space, and we find that the direction is not changed, but the magnitude is changed, and we can again draw the arrow which represents the direction in our case. So the 0 vector is 0 0, which is our origin. Of course, the most important concept of vector space is an additional structure called scalar product. Your vector space in abstract need not have any scalar product, but such vector spaces are not really interesting for physicists. Physicists need the concept of a scalar or dot product on the vector space. Formally, the scalar product is a function which takes the two vector uh, and convert them into a number. We'll not worry too much about this formal definition because this requires additional structure to be defined on your vector space, and then you will have to do, but we simply look at our example, and that can be easily extended to vector space. Let's take our R3 as our basic vector spaces. Let V and U be two vectors, that saying that V is a tuple V1, V2, V3, and U2 is a three tuple which is U1, U2, and U3. Now, the one of the scalar product which is denoted by V dot U with this vertical arrows defined. There are many other people, especially quantum mechanics people, use more fancy notation. I'll not use such a definition at present. Let's go ahead with the definition, and we have dot product between the vector is basically multiply the corresponding tuple and add them off. We take the first element from the two vectors, multiply them, add it to the second element, multiply them, add it, and take the third element and multiply them, and the sum gives the dot product between the two vectors. This is called the Euclidean dot product in the Rn. So for a given vector space, you may or may not have a scalar product. If the scalar product is there, you could have a multiple scalar product defined on the vector space. A vector space and the scalar product always goes together. So given together, they form a geometric structure, and that is what is the most useful in the physics. Most of the things get fixed only when you have a vector space and a scalar product. The Euclidean scalar product is one of them. You could have other things. In Rn, Euclidean, it's also called the Euclidean distance because we have seen that it represents the distance from the origin or the zero vector. The vector spaces with the dot product or the scalar product, they are called the norm vector space. Next important concept once you have a dot product is a norm of a vector or a length of the vector. Let V be a vector in a vector space with the scalar or dot product. The norm of the vector is denoted by this double line, and it is square of the norm is a dot product of the vector with itself. That is how the definition comes about. In our vector space R3, it is defined as follows. Let V be the vector in R3. That means is components of three real number V1, V2, and V3. The Euclidean dot product or the square of dot product is simply square each element and add them. So that is how the Euclidean norm is defined, and in this case we may call this a length of the vector 2 and or the magnitude of the vector. In the same spirit as we defined the direction and the magnitude, we already have a proper definition of the magnitude in terms of the norm of a vector, and we can also define the direction by dividing a vector by its norm gives a unit vector, and that we may call as a norm. So geometrically, let's go back to our example of a vector with the component 3 and 4, and we have we can calculate the norm, that is v dot v, square of the norm is 3 square plus 4 square, that is 9 plus 16, that is equal to 25. Norm of V is 25. This represents the diagonal of in this or the distance of this element from the origin. Of course, the direction or the unit vector, which you simply divide the vector by its norm, in this case, it would have a component of 3 by 5 and 4 by 5. Of course, to draw this is slightly difficult to get it exact. One of the ways is you draw a unit circle around the origin and simply draw a line connecting 0 in the direction of your vector uh, inside the circle would give you the components unit vector. So this is how you define norm of vector and direction. We will talk about more on scalar product as we go along.